Good evening and welcome to the Montshire Museum of Science. My name is Marco Staffney. I'm the executive director for the museum, and I'm also on behalf of Ledyard Brink, who's been sponsoring our Montshire Talks this year. We're really excited to have you all here for a wonderful conversation about science and culture. This year's program focus, Montshire Talks Frankenstein 200, helps to celebrate the 200th anniversary of Mary Shelley's Frankenstein, or the modern Prometheus. Mary Shelley, of course, captured all of our imaginations over 200 years ago as she really thought about how scientific innovation can sometimes turn its back on us or can sometimes go in directions that we never thought about. So tonight's program is going to delve deeply into that subject, where we bring you artificial intelligence and responsible design, featuring Dr. Eugene Santos. Dr. Santos is a professor of engineering at the Thayer School at Dartmouth College. His work intersects the areas of information, cognition, human factors, and mathematics. His current focus is on dynamic human behavior, intent, inferencing, and decision-making with an emphasis on learning. So please help me welcome Dr. Eugene Santos.
Thank you very much. I'm looking forward to talking to you folks and hopefully opening a discussion about even AI in general. I'm going to preface this talk along the lines of I'm going to try and give you some ideas behind what AI is. Not going to necessarily right now start off talk as much about Frankenstein, but keep that in the back of your head. So let me go ahead and just start off. I'm going to try and talk about 3 different artificial intelligence events. So these are events that I was personally very interested in, but I believe that they can lead to certain concepts that gives us some notion of what the technological advance was, how is the algorithm really working behind the artificial intelligence, as well as potentially lessons learned that we draw from it. Let me caveat the following. AI is extremely broad. You're probably also seeing nowadays, anytime you see a news article, everything is AI. Yeah, you could say that, but it depends on your definition. I would like to say it this way. Anything that is helping making a decision or making a decision on its own is an algorithm, hence it's AI. It doesn't have to be very complex. And I'll intersperse some other examples, other discussions throughout the talk. But as I said, one of the things that I want to take the 3 examples, tie it to 3 concepts, and those 3 concepts hopefully will at least give some sort of foundation of what we want to talk about also in responsible design. So let me go ahead and get started. The very first event, or let's say AI artifact, was something called Genghis. Genghis was an early robot built in 1989. It was built to emulate an insect with 6 legs. I have a very personal interest in this one. I wish I could say that I was one of the people who worked on Genghis, but at least I had the opportunity to watch Genghis in action. So I was a young graduate student at Brown University doing my doctoral study in cognitive science, natural language processing, AI, sort of all those mixed together. And I got to attend the American Association for Artificial Intelligence conference that was held in Boston that year. And that was the year that Genghis, I wouldn't say Genghis debuted that year, but one of the achievements of Genghis debuted. Let me just jump ahead. The achievement was Genghis learned how to walk. This is what this segment is going to talk about. So a couple of elements. Let me describe Genghis. Again, this is 1989. Genghis was something called behavior-based robotics. Behavior-based robotics was trying to describe how you take small behaviors and aggregate them into larger behaviors. What do I mean by that? Let's take our finger. Our finger has multiple joints. At least this finger has a couple joints. You have different actions, like, okay, I can bend my finger on my first joint. I can bend the second joint. I have the combination of the 2 joints moving, and then all these things, right? So you can imagine that the behavior is really looking at some very simple actions at each position. Now, the combination becomes very interesting, right? They have meaning for us. Now, what's the challenge, though? If you look at all the combinations, and officially you can call them degrees of freedom from all these actions to combine, many of them don't make any sense. They could be just simply spastic movements or something. So the challenge for Genghis was, how can it learn to control all its legs so that it actually walked forward? How do I develop an algorithm to do something like that? So the basic ideas were, can I learn what to do with positive and negative feedback? That is, am I doing the right thing, am I doing the wrong thing? What can I do in terms of figuring out when should I activate behavior? So what does that mean? So let's take one of the legs. Let's take that right front leg. When should I raise the right front leg? When should I sweep it forward? It has to figure that out. The other elements, I'm now trying to build an entire behavior control system. That is, what is the behavior control to make it work, and can I learn it through experience? So the idea is, it's a very classic thing. It's like starting with nothing, let it figure out how to walk in the end. So when you learn each behavior, then it becomes part of the active control. Now, let me just describe then just what Genghis was made of. Again, remember, this is 1989. Genghis was a six-legged robot. It actually limited the number of controls it had. So that's why it says only 12 behaviors and 6 conditions. Don't worry about that. It's just saying that even that simple problem was already a very tough problem. I, as well as many of my classmates, even my advisor, says that this is really hard. I don't think we can do this yet. So what happens is the following. Let me just give you a description of what, a description of what I remember Genghis doing when I watched the actual demo. They wiped the memory of Genghis, so no information. So Genghis first starts flat on the ground, and you could see the legs flailing randomly. And then after a while, as its legs are flailing randomly, then you start seeing that, from the feedback of, say, not getting anywhere, being bad to be on the belly, and I'll describe that a bit more detail later, it then starts coordinating the arms. Why is that really cool? There was no pre-planning. Why should this leg sweep forward, sweep back, then this one sweep forward, sweep back? If you could think about how an insect walks, okay? Now, here's the key picture. What the authors did, the research behind it, and the researchers were Patty Mays and Rodney Brooks. Some of you may have heard of them before. They're very early in robotics. This is a figure of Genghis, and you can see here's the legs. And the reason I wanted to put this schematic up was the feedback positions. So there was 2 feedbacks on the bottom of Genghis, which is our negative feedback. This is the belly. So if the belly touches the ground, or either one, no, we don't like that. So the basic idea is that if I get a negative feedback, don't do that behavior. Now, the one thing with the positive feedback is this wheel. So what Genghis had was a string, or actually it was a wire that fed through that wheel so that when Genghis moved forward, it unspooled the wheel. So it's a little nice trick that, hey, Genghis is moving forward. That wheel is spinning. So that's a positive feedback. So based on those elements, there's a couple of things, and I'm going to simply to talk about the complexity a little bit. Genghis could swing its leg forward, push down, or lift up. Okay, and then sweep this way also. For each leg. I didn't mean to do both legs at the same time. Simple principles. Simple learning principles that, first of all, you had to be relevant. You want to make sure that your behaviors that were correlated to the positive feedback and not correlated with negative feedback. Very, very trivial. Another simple idea, you want to be reliable. That is, all of your behaviors receive a consistent feedback. So the idea is that they wanted to somehow take that feedback information and then update all those behaviors. Now, a little bit of more information is that these behaviors, there was a simple structure, is that to perform a behavior, you need to figure out what were the necessary preconditions behind those behaviors. So a precondition is like, my front sensor is reading this, my leg is in this position, bent this way. If that's true, then I can execute a decision. Okay? Now, from all that, this is just one of the demos of how Genghis, unfortunately I don't have the original one where you see it flopping around, but this is Genghis moving. And if you keep watching the video, it'll get to a point where they even trained it to, say, try and cross over an object, try and navigate stairs and such like that. But the idea is that, we can develop an algorithm to do this. Remember, everything had to be computational. And before I forget, what is the definition of a computer algorithm? A computer algorithm is a finite sequence of instructions that are given to execute something. Okay? So it's very, very specific. Here's one thing. Let me now refer back a little bit to Frankenstein. Algorithm versus Frankenstein. You have to tell a computer exactly what you want to do. And it'll do exactly what you want to do even though you didn't want to do it. Okay? Everybody knows this. So how do we do something like that? So why does this work? Let me point to the following. Let me go back to this picture and just this notion of the different feedbacks. Personally, I thought it was really cool. One of the nicest feedback was just that simple idea of the wheel trailing there. Very simple insight just to capture that measure. But think about it for a second. Having restricted to that wheel and those sensors, actuary defined what Genghis's goal had to be. Genghis's goal simply had to be move forward somehow. Move forward by not sliding on your belly. Right? That would be the immediate interpretation. So, what point do I want to make from that? The point I want to make from that is that it is about defining the goals for the AI algorithm. The AI algorithm is trying to achieve something. Now, this is a definition of goal that I pulled from Merriam-Webster. And you can see all the elements. You know, the goal is an end toward which an effort is directed. It could be called an aim. And then you have the other ones, like maybe it's an area, an object of which some player must reach, like you're trying to figure out how to exit a maze. All of these are various different definitions of goals, and you'll see them across pretty much every AI algorithm that has a particular purpose it's shooting for. Now, I'm being very mealy-mouthed about having said that. Some people do try and build algorithms where they have either one, no idea what the goal is, or they try and actually be goalless. I'm not going to talk about that as much. That is how should I say, a bit of a tough subject, because in the end, because it's a computer, there's still always going to be a goal. All right? Now, let's think about some of the goal examples. I know this, I just realized this is really small. So the first one is, how many of you here have heard about deep mind and playing Atari games? This was actually a very recent event. So I don't know if folks remember, Atari was one of the early game consoles that we could buy in our homes, and we could play everything from, hey, this is the Space Invader machine, this is the old tank games, you know, sort of two-dimensional pixel games. This, if I'm not mistaken, I believe it was, yeah, it's about around 2012, 2013, they were able to play a whole sequence of Atari games and beat them. Okay? So you can imagine that, but what does that all mean, though? What does it tie back to the goals? Well, the goal was they looked at the score that the Atari game was providing as feedback. And then they chose their actions for each particular game, whether it's the Space Invader game or whether it's an asteroid game. Some of you may know what these are some very, very classic video games back then. And looked at the screen, looked at where things were sitting, and then looked at, if I move here or I take this action, how does that change my score? Or does it end up with a game over? Other straightforward goals? Well, think about Deep Blue versus Kasparov, right? The chess grandmaster who in the second play lost to Deep Blue. Also very goal-driven. Those of you who might know something about game trees, Deep Blue basically used brute force to calculate all the possible moves, but also at the same time, if people read through, Kasparov sort of psyched himself out also. But regardless of what was behind all that, it was still goal-driven. The goal of Deep Blue in playing the game was, what is the best move it could make, and also marginalize any of Kasparov's potential follow-on moves from there on out. Here's another one that you've probably never heard of. This was developed around 1995, so it was fairly early on. This was for the Boeing 777. This was actually for designing and controlling the cockpit of the 777, because that was one of the new planes that were coming out then. It was one of the most sophisticated cockpits of the day. You can read everything that Boeing said about it. But what was really interesting was that they built the design and control system using AI technology. The goal was, how do I schedule the transfer of information between components and cockpit? And you can imagine the complexities of a cockpit. How do I schedule, you know, when a control is sent by the pilot in the cockpit. Where does it transfer to? This was actually a fairly large-scale result for artificial intelligence, at least on the scheduling side. But again, there was a goal again. The goal was designed that you have to operate within these specified parameters. So, other things you could think of, just in more general without examples. When Amazon makes book recommendations to you, when Spotify makes your daily music mix to you, all of those things have a goal in mind. Now, think back again. This is an algorithm. Since it's an algorithm, you have to be precise. You have to be able to compute those particular goals. Now, where do I want to lead from here? If we're talking about goals, again, sorry, it's so small. If you're talking about goal, it could be a lot of different ones. So I'm going to generalize the classes of goals and then kind of discuss what are the impacts of them. One is just to acquire information. You know, if I'm just, my AI might be, go out and collect all the personal user data, and I'm not going to get into that argument. Collect all the personal user data in the world that you can, because what I want to do, my goal is to figure out how people cluster together, right? Your friends' networks. You could have other ones, such as, I want to just explore the environment. Imagine what might have been science fiction, say 30 years ago, a search and rescue robot, right? A search and rescue robot has to explore the scene. They have to go around and figure out where are possible victims, where are the possible dangerous points. Those are all goal-driven. It needs to figure out, that if I go this way, is this a good way to go? Is it something I need to do? Again, those are all defined. Some of you may have heard of the term. I'll drop some terms around reinforcement learning, stuff like that. If it's something that catches interest, feel free to get in touch with me. I'm happy to point you out to various information portals on these. Now, you can also do this, and this is sort of back to that goal listing. Your goal could be just simply be random and unpredictable. Just do something so, you know, it may kind of make sense. I might want to build an AI to jink my fighter plane around, make myself a harder target. Human beings, and I know I suffer this, whenever I try and generate random numbers, my students say, why don't your numbers have any 4s in them? I don't know, but that's my random number generator, so it's not so random. So you have the computer become unpredictable in that way. So that is also a very valid goal. The point of all this is that two things. One, even with the goals in mind, is it possible to discover something novel? Is it possible to do something novel? I just want you to keep that in the back of your head. I mean, what does that mean? We'll come back to a little bit of that later. When we talk about novelty, of course, it then leads to, is artificial intelligence, the way I just described now, intelligent? We can have days of debates on that. All right? And that's why I kind of caveated that. I made my definition of what artificial intelligence is, that something that at least comes up with a decision. So it could be something as silly as that, hey, if it's greater than 35 degrees, then I'm going to go jump in the pool. That's still a decision. Now, as long as they are computable, hence you want the AIs to have these computable goals. Now, let me bring up the following. Let me just bring up these pieces. This element down here, what governs when, where, and which actions to take? That is, remember, there's the goal. The computer, the algorithm, the AI wants to satisfy this goal. How should it go about achieving it? That's when we have all the questions that, does the AI really know about the consequences of its actions? Right? Is the particular action it takes necessarily better, good, bad? You could throw all those questions into it. The AI is an algorithm. Unless you've somehow specified the notion of, is this a better action to take? Is this a worse action to take? The AI will just simply take it. Now, is that bad? Is that good? I'm going to say it this way. It just depends on what you've accounted for as the designer. So that's why I want to bring up goal, is that you know that you've designed a goal, but there's also the elements that surround the goal, which is the actions, behaviors that bind that goal. Okay? Now, I'm just going to bring up a couple quotes that are recent and relevant. One of the folks out there, and you know, you've seen the whole discussion about, you know, AI is the most dangerous thing to come in the world. People who are pro, people who are con about that. One quote that I thought was kind of illustrates this whole notion of what I'm talking about in goal is Stuart Armstrong. Stuart Armstrong was one of the people in a book he wrote called Smarter Than Us that was worried about the AIs. He has this one simple example. So let's say we have an AI that we've given control to help manage our economy. So as you said, if you ask the AI to increase the GDP for your country, you know, one of the actions the AI could take, burn down several cities. Why? Because after you burn it down, you get to rebuild them, which then would increase spending, which would increase GDP. So that's saying that, hey, the goals, you know, yeah, those are something to shoot for, but that other mechanism is maybe something that we have to, of course, think about. One other slightly, how should I say, another comment that's slightly more broad, which also reflects the area of things, is Stuart Russell. He's a professor of computer science at UC Berkeley. He had said something along the lines is that right now we are pouring billions of dollars into AI. However, we have no idea where we're going or what we're going to end up with, which is also true. Because, right, I don't want to necessarily just call it the hype, but people are just jumping into it. And then let's just try all these things. Let me come up now and move to the second event. Google Brain. I believe that probably most of you have heard about this important event. So around 2012, 6 years ago, Google Brain, which is a giant neural network, and that's why they're willing to call it brain. And actually, it's not a human brain. It's a simulated brain based on the theories of neural networks. The amazing thing was they took millions of images, gave it to the brain, didn't tell the brain anything about those images, and they were able to extract the concept of a cat. What I'm going to do is I'm going to try and describe how this sort of happens, and of course, then there's another concept that's going to be tying to this. So what is happening with this? To the right is the hottest technology in AI right now. Deep neural networks, deep learning. What is a neural network? A neural network, in its simplest form, is that you have a bunch of nodes which people philosophically can claim that they may be brain cells. You have connections between the nodes, which would be potentially how brain cells send signals to each other. But in the pure computing sense, each of these nodes are a simple processor that would take a signal, an input signal, process it, and then pass it off to the other networks, other nodes, and even potentially subnetworks here. What does it mean to train a neural network? And what does it mean to train a neural network where it's something called unsupervised learning? That's basically just throw things at it. Don't tell it what this is. So some of you can already, you know, if you look at statistics, if you use statistics and you have things that are known, so it's okay, here are my examples of cups, here are my examples of cats. I can use statistics of different features that I get from the pictures of them and make a decision. Here, nothing. I just say, here's a whole bunch of pictures. What a neural network can do, or you could use a neural network to do, is a basic idea called an autoencoder. An autoencoder, just as I said, I'm just using their terms. I wish I could find a simpler than one. An autoencoder, you could say it's this way. A neural network, here you have the inputs at the bottom layer, and then you have a whole bunch of outputs at the top layer. Typically, those outputs are telling you, if I was doing the ones where I already have labeled cups and cats, the output would be output whether it's a cup or it's a cat. But an autoencoder does the following. You take the image as input, so let's say image number 546 as input, and as output, you also want to see image 546. Wait a minute. Why? What are we trying to do in that? The thing we're going to try and do in that is that there's all those middle nodes. you can imagine that there's so much computation going on. And if let's just make this simple. What if all those computations are random? You can imagine there's random functions, random things that get passed through that if I take that original image and this is all random, I'm going to get garbage at the output. The goal of the neural network is that can I find and train, that is learn the functions that are going on inside and have that image go through and pass it out again. Those of you who know simple math is that why can't I just build an identity function? Sure, that's the easiest function. If I build an identity function, every image I learn I'll output again, but it doesn't tell me anything. If I get a brand new image, it'll just output the brand new image. What's the key? Let me simplify it. Let's take that bottom input node, input layer of nodes. What's input in them, just to make it more concrete, would be, for example, each pixel, whether it's on or off in the image. Same copy of the output layer. But what I'm going to have in the middle, let's say that bottom layer accounted for 4 million pixels. Top layer is 4 million pixels. Let's make it extreme. My middle layer where functions are happening is 100 nodes. I go from 4 million to 100 to 4 million. Hopefully I should be triggering and says, this is what autoencoding means. I'm trying to find a way of, you could say, compressing the information from this layer input, coming up and recovering it. Some of you may know of things like video encoding, image encoding, JPEGs, all those things. Sort of a similar idea. But the idea is that if I can learn that concept, then I've encoded that knowledge. That's what makes neural networks magic. They can come up with a function to do that mapping. So with that, though, I don't want to belabor too far. One of the things they have is that I reason put it this small because I don't want to describe that. That's a really awful looking function. That's actually their goal. So I'll just point that out for a second. The goal is to compute that optimization to get your proper functions. Now, here's one way of looking at this. When you take that input layer and you want to have things come out on the top, you can also talk about the following, is that output layer, look at the nodes or the neurons that are most active. So if I've passed in, let's say, 1,000 face pictures after I've trained the neural network, then I want to look at this, what in general were all the most active nodes? So that top one where, hey, with all the face pictures I've passed in, this is what the network learned. This is potentially looks like a face. These two, yeah, we can't see as much. But if you imagine very carefully or stare very hard, you can see sort of a cat here. This would be a cat feature. So, sort of here's the face, here's the 2 ears up top. What's this one? This is supposed to be a human body. So you sort of see a head here, sort of see a body, a little bit of the arms. That's the abstraction. So what did it mean to learn a cat, a face, or a human body? Is that when they took all the things that were cats, it produced this. When it took all the things that were faces, it produced that. And then what was really interesting, when it passed a new image it never saw before, then it would come back and say, is this a face? Is this a cat? Okay? All right, sure. This is all the neural network magic that's going about. But let's talk about the following. This is one of the images of information they pass through. Here's all the faces, right? It's a collage. These are the faces that it determined as faces. What the heck is that? So it considers that a face. Let's do it for cats. I just took this straight from a research paper, so forgive me if I'm making fun or abusing the researchers. I'm not. We're just having a discussion, and I'll deal with you guys later. Anyways, this is a cat. That, to me, looks like a Starbucks coffee. Wow. It says, somehow, that magic encoding of the functions came up with this. Here's a really fun one. Shortly after the Google brain did the cat stuff, other people start playing with it. The MIT folks decided to say, how well is this really working? So you can see from the title, the MIT was able to fool consistently the Google brain into believing cat was guacamole. It was somehow, what is actually being mapped around there? Why do I have a picture of a turtle here? This is actually a synthetic turtle. It's a plastic turtle that also, as part of their experiment, they trained that this turtle was a rifle. Okay? The moral of this particular element is that we don't know what the heck that's doing. We get some great possibilities that, hey, something is happening, something is being learned. But what does that mean? Now, if you think about it, this is a computer algorithm, right? Everything, we have the steps laid out. But you can imagine that the complexity of math is pretty bad that, yeah, okay, we're not sure. But there's analogs, of course, to human beings as well, right? How many times have you had friends, relatives, or little kids identify something you never expect them to identify as X? I don't know. I'm not going to posit whether there is a direct biological relevance between what you see in the algorithm and this, but at least it maybe starts us toward understanding these things. All right, I digress too far. Here's a bad one. People may have also saw this news article. Not long after also, it was shown that, you know, in certain instances of people who were passing pictures in the Google Photos, they were identifying, you know, African American people as gorillas. What is going on here? What is going on here was simply the number of images that were in the training set were biased. It's not that they were deliberately biased, it's what was available. If all I have available is a million chairs, everything's going to be a chair, right? So the second concept is knowing about the bias. Trying to get a handle on this. In this case, this one is very hard, although you might be able to argue statistically there are things that we can figure out. So with that bias, all right, what is the cost of bias? What is the cost then of making a mistaken decision? So some of you can already, you know, think about this, is that this is not, and this is just a simple classification problem. This is a classification problem that would then allow you to make decisions. Let me give you a simple example that happened in real life. And I'll also caveat, this was not using an AI, but hopefully the story relates. So a young man of Asian descent was suffering from severe nausea, pain in the midsection, and elevated liver enzymes. Those of you who may have some medical knowledge can already start guessing what some of the illness was. This person, though, ended up being diagnosed as having hepatitis. Those are all the symptoms. But partly the most telling one was that the person seemed to be suffering from jaundice. Okay? All right. Two things. One, jaundice. How are they determining jaundice? This person's of Asian descent. Their skin tends to be already yellow hue. And I'm talking about, you know, Asian Chinese, that Asian. Second thing, and these were the human doctors. There were three elements that they looked at that ruled out this other disease. This other disease being acute cholecystitis. I'm sorry, it's gallstones. Okay, acute gallstones. And there was three factors that this person didn't meet. Over 40, it was a young person. Female, this was a male. And fat. They called it the 3 Fs. The reason I want to bring up the example is that, hey, that bias pushed them in the wrong decision. So the treatment they gave for the hepatitis was completely wrong. Those who know about gallstones don't give the person even more fatty foods. So the person ended up suffering for much longer than that. But the point is that that's back to the bias. It's being able to come back and identify that you do have that bias, so you understand the range of errors that might happen on that. So that's the second concept. Now, let me drop down to the third event. 2013. This made, of course, headlines. There was a tweet that Barack Obama was injured in an explosion in the White House. This came through the Associated Press. Those who might remember the incident know that this actually was a fake tweet. Within minutes, and actually I think the time elapse was 9 minutes, within 9 minutes, AP on all its other social media platforms says that this is fake. We've been compromised. Ignore anything that's coming out of the AP. Okay, all right, this is a hacking event. How does this relate to the AI events itself? I'm not saying the hacker was AI. For those of you who might have read, the people who claimed credit for this hacking event was the Syrian Electronic Army. I think I said that right. But the consequences, if you also remember, was a flash crash. Within that small amount of time, and you can see right here it really says 1:10 p.m. So the tweet came out at 1:07. AP corrected itself at 1:16, and then in that interim, we had the flash crash where the Dow Jones dropped over 100 points. At the same time, of course, with the S&P, they dropped, and within 3 minutes, it wiped out $130 billion in assets just from that one item. How does this tie back to the AI? Those of you who have been following know that, hey, this had something to do with high-frequency trading. Because in those small times, pretty much all humans or human traders didn't believe that that was an actual event. Because why? We have some of the built-in things that this was only one news item. Yes, it may have come from AP, which is one of the most respected ones, but nobody else was picking up on it yet, right? CNN didn't say anything. Nobody else was saying anything. And then it came out and fixed it. So the likely culprit was high-frequency trading algorithms. So the high-frequency trading algorithms, and I'm not going to read that, you can already guess, is that they are very complex algorithms. I don't know what goes in them, so please don't ask me. And a lot of that's trade secrets, of course, for the people using it. They're very complex, running on some sort of factors, analyzing all the information around. One thing I can say, though, I was involved in a project that was trying to analyze deception and high-frequency trading. So part of that flash crash, trying to understand why those affecting, can we detect it? Thomson Reuters actually makes a whole business out of trying to analyze news as fast as can and how the markets react. So one of the terms here would be looking at things like sentiment analysis, right? I'm pretty sure every one of you have heard about sentiment analysis. Is about, hey, what is the prevailing feeling about X? And they apply it to markets. I know that they have tons and tons of data because they process all the new stuff. What do you feel about IBM? What do you feel about GE? So within that is all AI technologies as well, because you can imagine they're taking all, forgive the cheesy spinning AI, that was the best I could do on PowerPoint. But regardless of that, that is all the AI is going on now. But what do I want to talk about from this? Here's the thing. The third concept is situatedness. Situatedness you can describe with 3 elements. First element is that it exists, or the agent, so the agent, algorithm, AI, I'm going to use those interchangeably, exists in a dynamic, rapidly changing environment, which this case it was, right? This is a high-frequency trading domain. Second element, they can manipulate or change the environment through their actions. Sell orders, buy orders, sell orders, buy orders, right? And they're making decisions on that. And third, they can sense or perceive. What does that mean in this case? They're getting input from the environment. They're watching what's going on. Now, here's the thing, though. If we take the concept of situatedness, well, it knows it's working there. But what's missing from the high-frequency trading algorithms? It has no notion outside of the environment it's working on, right? Because just imagine any computer program out there that say, I'm working an API for this car. I know these are all the actions I can take from a car, and I know these are all the sensor readings the car is giving me. But I don't know anything else outside the car. So what's it missing? It has no idea of the consequences of its actions, right? What it does know, though, and this is what bears a lot of exploring. What it does know is that when it does take an action, its local environment is changing. And at least that's an indirect reflection of what's happening outside, right? So by its sequence action, suddenly the stock drops. It will see those values. What do we do from there? Open question. But it's to realize, though, that what are your ripple effects? When you take an action in the environment, what is the ripple effects? Is that true situatedness? If you want to build an AI that's situated and understands, then I think it also has to understand everything outside of it itself. One other thing, though. Let me just jump to something philosophical, because after I talk about situated, I also personally believe that that's a necessary condition to actually be an artificial intelligence. Two things, and this is me standing on a soapbox right now. People say machine learning is artificial intelligence. No. Okay? You look at the Google brain, right? The Google brain is not situated unless you apply it somewhere. If you take the Google brain and embed it as a larger system, then yes, that's situated. But I want you to just keep in mind, that's what separates machine learning from AI. Situatedness is that necessary condition. But, of course, machine learning is a subset of AI. All right. Let's briefly now tie these three together. The three concepts: goals, biases, and situatedness. Responsible design, at a minimum, has to consider these three elements. You could, hopefully I've stirred a lot of thinking just by those three events. And what are the things that can go right or go wrong? They give you, hopefully, lessons learned. But if we can think in terms of an AI algorithm, where they're situated, what are the things they're likely to miss, and then how did we define those goals? That's an important step, trying to be responsible when we release that AI out to do certain things. Now, every one of these, you could already see. I may have chosen Genghis the goals, Google Brain the biases, HFT to situatedness, but all the different pieces apply, right? One thing I'm going to add on top of that: complexity. You are hearing day in, day out now, where everywhere you can use AI. Some from very minute things like, well, actually, this already occurred like 20 years ago. Anybody ever heard of the fuzzy toaster? The fuzzy toaster was using an AI technology to give you the perfectly toasted slice of bread. But what do we do now? What we want to do is start linking up all the items in your house. We heard about the MIT media that has been pursuing the smart home, connected home, but it grows even bigger. So if we look at this, and don't worry about reading, here's this. You could say that this here would be the larger scale connected home. It's controlling everything that you have. Now, take that even one level higher, where all the homes in a neighborhood are connected together. All the neighborhoods are connected together. And the idea is that, I can do a lot of things that would improve efficiency, improve energy consumption, even improve flow of traffic if I have something like this. Now, let me give you a very simple example. Who knows about the Morris worm? This is a historical event. 1988, the Morris worm. The Morris worm was the first computer worm, so to speak, first computer worm to attack the internet. Actually, it wasn't designed to attack the internet. The Morris worm had this incredible ability, because it exploited back then, weaknesses in the machines, how to get to a machine, download a copy itself, run, and then spread to other machines. Wow. Imagine that the person who deployed that, you could read lots of stories about Morris. Morris is a professor at MIT now, okay, despite having a felony conviction. It's a fun story to read. This was 1988. But you could think about this, that what was the impacts of releasing it? People even say things like, what happened is that when it took over a machine, it actually had one fatal bug in the worm code. The worm code would keep duplicating itself, even if it's already infected a machine. It screwed up. So just a small computer bug. Which means what? You can imagine it, worm. It's like my computer now has to try and run 10,000 worms, let's say in modern terms. What does happen to your computer? Your computer goes down or just freezes. So he ended up, that the damage caused was freezing all these machines out there. So there's actually some wild estimates, because nobody back then could know how to compute what the problems were. But I think the Government Accountability Office, the GAO, says that it was between $100,000 to potentially $10 million back in 1988. That was the damage. And now we hear, of course, all the virus stuff. But the point I want to make about that is that there's a complexity there. Even in the simpler ages back then of the internet, you didn't account for that, right? So if somehow we could, and actually that's the real challenge question, how do you, visualize what can happen further? Then, of course, we have all these things. Complexity of autonomous vehicles. I'm not going to describe the tragedy of what happened at Uber, but this is somewhere we're all getting to. you have these huge swarms, huge collections that they now have to interact. So from this, you could see all the damage and all the disasters that might happen from it. And these are what a lot of the people who worry about consider. But also, a lot of us in AI, I tend to be on the con side that I don't think it's going to be a lot of damage, because I know what the limits of the computer are. I know what the limits of the AI algorithms are, as long as I'm conscientious about when I've deployed it. Not an easy thing to do. It's more of a philosophical thing. But let's take something that most of you have probably read about. Asimov's laws of robotics, right? That keeps coming up over and over again as AI keeps growing. What were the three laws of robotics? Let me make sure I'm reading them properly. So the first law of robotic is a robot may not injure a human being or through an action allow a human being to come to harm. Another one, oops, sorry. You can't scroll down. Oh, here it is. Another one is that a robot must obey the orders given to it by human beings, except where such orders would conflict with the first law. And then the third law, a robot must protect its own existence as long as such protection does not conflict with the first or second law. What's the point of that? The point was to try and define constraints to try and bound the behaviors. This is actually, it's kind of a beautiful idea, right? It's an external constraint that if I can bound on the AI system. How do you achieve it? Don't know. It sounds great philosophically. Try and implement that in a computer. What would you need to account for? Something to shoot for. But let me give a counterexample. HAL 9000, right? Space Odyssey 2001. Those of you who remember, especially from the novel, from Arthur C. Clarke, what was the problem in HAL? HAL killed off all its crew. But if we think back to the whole notion of the goals, HAL figured out the best way to satisfy his goals was to kill the humans on board. But why did it take that final extreme goal? Because the constraints put on it were contradictory. The three laws of robots seem to be not contradictory because they're ordered or something like that, but how could you come up with the right set of constraints that doesn't happen? Human beings? Yeah, when we hit a contradiction or hit something, no, you can't do that, but you have to do that. We somehow work through that, and boy, what does that open up to? All the philosophical discussion, all the angst, all the things what's the right thing to do. Imagine trying to computerize that. But hey, I think that's something that, for me as an AI technologist, that's something we should be heading towards anyways. So let me see. One last thing. Oops, sorry. That I want to bring up is, let's go back to Frankenstein. So I'm just going to do a short, pithy ending. Back to Frankenstein. Let's look at the three elements. Frankenstein, of course, is not a computer algorithm. But what makes Frankenstein so scary? The goals are unbounded. The biases are unbounded. The situatedness is unbounded. It's the world. So what's that saying? The monster was as human as the rest of the humanity that the monster was placed in. So anything was possible. That's the scary part. Where AI comes in, I'm going to say this. AI is bounded. One last kind of food for thought. This is more on the fun one. When I talk about intelligence and creativity, let's see. Hopefully I can switch this properly. You already saw, I'm talking about, this is some recent results about AI and music. So this is music that was completely composed by an AI. And what it did was that it inputted a lot of different Irish folk songs. And now granted, these are human playing it, but the AI did the score and the arrangement from what I understand. Yeah, there's a little bit of strange things in it, but if you imagine, that can sound like an Irish folk music, and it's original. Now what happened to creativity? Where's the bounds and the lines? If we can be creative, then that goes back to that one sentence I had about novelty. If now we start talking about novelty, oh gosh, are we even worse than unpredictable? Now what do we do? let me just give up one other last video. This one I found kind of fun, because I actually found this one in some ways more haunting. I don't know if people have known about this one, and I'm going to caveat it. Can I turn up the, oh yeah, here it is. This is original composition, supposedly done by a computer, derived from all the Beatles musics. Caveat. The lyrics, though, were written by a human being. Okay? But the score itself, the music, that's pretty Beatlesque. For those of you who love Beatles now, those who truly love Beatles can probably find this. There's some really screwy things going on. But that's a scary thought. And I close with that. Thank you very much.
This is where I get to ask you some questions, because so in your pithy ending about Frankenstein, his unbounded world, unbounded rules, unbounded goals. So I was thinking, for those who are not familiar with the book, Frankenstein's creature sort of is born into this world and develops rapid consciousness extremely fast. He goes from being sort of a wild wolf cub in the woods to reading Goethe and reading French and German within a few months, just from sort of almost osmosis and looking at books through a window. So in that, he does end up getting some goals, and his major goal is destroy Frankenstein's life. So yeah. Frankenstein, if you're not as familiar, the monster is not called Frankenstein, it's just the creature. So the creature needs to destroy Dr. Frankenstein's entire life, and that's the whole goal. So within that, like, can you program morality?
That's the open question. What does morality even look like? Can I even represent it in a computer? A computer is just bits, right? If somehow, here's this. What leaves me hope that we might be able to program morality is, what are we representing in the world? Can the world and morality be reduced to bits? Now, of course, that's the big question. But there's a lot of things we've been capturing. The reason I brought up these very last things is, I didn't think creativity could get that far. AI in music has had a long history. So even back in that 1990 meeting that I attended, I was already listening and said, this is one of the first AI-generated compositions. It was awful. But they were trying to make the first move on that. And it's like, Here's the one key, though. With the music and computers, it's really about our perceptions of them and how we interpret them. Right now, computers don't have any interpretations. Can we make the way we interpret the world computational? If we can do that, then we can make the computer do that.
So how hard is it to create nuance? So you said, we have an articulated joint, and you can point this way or you can point that way, but they all mean different, like different hand motions mean different things. What would it take to really program the nuance between a finger wag and a point?
The straightforward approach right now, show it all the different ways of doing it. And that's what becomes killer. It's unbounded, right? Because, I'm going to say this. Early on, when they were just trying to do image recognition, is that a chair? Even a simple problem where the chair was slightly rotated. Those of you who've worked in this area know that that's already been solved. But early, when it was slightly rotated, you couldn't tell that was a chair. So what they had to do is show every orientation of the chair until somebody figured out a really neat way that, hey, I can somehow mathematically represent a chair invariant of how it's situated. But with the finger one, if they each have different meanings, I wonder if this is an appropriate example. Everybody knows, and hopefully I'm not wrong, how many different words for a snowflake there are in the Alaskan Inuits. So forgive me, I'm drawing trivia from my head. So there, right, you have to define all the possibilities and then match up all the patterns. So if you have infinite variations, though, that starts becoming problematical with machines.
And furthermore, in terms of our human condition, cultural definitions too, I imagine. So a point in one context or one situation is different in another. Well, you've given us a lot to think about today. I just want to give you a big round of applause, and if you could thank Eugene Santos for today.